Okay, so we're going to look at some example problems for sampling distributions. Um, so this problem here says, suppose that a random sample of size 64 is to be selected from a population with a mean of 40 and a standard deviation of 5. So we've got our sample size is 64. Our mean, we know, is 40, and our standard deviation is 5. Okay, so what are the mean and standard deviation of the X bar sampling distribution? Describe the shape of X bar sampling distribution. Okay, so for A, we know that the mean of our sampling distribution is the same thing as our regular mean. So this is just going to be 40. We know that our standard deviation of our sampling distribution is the standard deviation over the square root of n. So we just need to replace these. So we've got 5 over the square root of 64. So if we replace 5 for 64, that's the same thing as 5 over 8, which that should be 0.625. You could use 5/8 or 0.625. Does not matter. I'm just going to leave it as 0.625. And our shape, because it doesn't say that the regular population was normal. So we don't know that, but because our sample size is greater than 30, then we're going to say that the shape of this is going to be normal. Now B says, what is the approximate probability that X bar will be within 0.5 of the population mean of the actual mean? So what's the probability that X bar is going to be within 0.5 of the mean of our regular distribution? So what's the probability that it's between 39.5 and 40.5? Well, we know that we're using a normal distribution because of this. You can't just assume all the time. But in this case, it's safe to assume because our sample size is large enough. So this is going to be, we're going to use the normal distribution. So we're going to use normal CDF. Our lower bound is 39.5. Our upper bound is 40.5. Our mean is 40. And our standard deviation, we have to use it for our sampling distribution, which is 0.625. So how is this going to look when we type everything in? So turn on. Okay, so we go to second, distribute. We use our normal CDF. Yours may look a little different, but you should type it in the same way, 39.5, comma, 40.5, comma, our mean, which is 40, and our standard deviation, which is 0.625. And so, just within a very, very small amount, we're going to have 57% of our data is going to be, 57.6% of our data is going to be within 1/2 of a number, so 0.5, of the actual mean. So that is, and that's very good. Obviously, you see that even though our standard deviation of our normal distribution, of our regular distribution, sorry, is 5, even shrinking that by 10 times as much, because we have such a large sample size, we're going to be capturing a lot of our data. So you should have 57.62. And lastly, it says, what is the approximate probability that X bar will differ from the mean by more than 0.7? So this is a little different, right? It's on the outside. So it says, what's the probability that X bar is greater than 0.7 more than the mean. So that X bar is greater than 40.7, or X bar is less than 39.3. So because we're now looking, instead of looking kind of on the inside, we're looking on the outskirts of our distribution. So what we can do is we could find the inside and then subtract it away from 1. So this is going to be the same thing as 1 minus the normal CDF of our lower bound, which is going to be 39.3. Our upper bound is 40.7. Our mean is 40. And our standard deviation is 0.625. Sorry, running out of room. And so this number, again, we're going to go to our calculator. And we're going to say, okay, second distribute, normal CDF. And that is, 39.3, comma, 40.7, comma, 40, and 0.625. And so the area in the middle is 73.73%. And we do 1 minus that answer. If you ever want to pull up an answer, you can just do second and then the negative sign. And then that will give you 0.2627. So 26.27% is going to be our answer for this problem. So 26.27, 26.27%. So that's how we can use this. So basically it's the same as using the normal CDF before, but we have to just alter our standard deviation based off of our original and our sample size. So the next problem, in the library on a university campus, there is a sign in the elevator that indicates a limit of 16 persons. So only 16 people can get on the elevator. In addition, there's a weight limit of 2,500 pounds. Assume that the average weight of students, faculty, and staff on campus is 150 pounds, and that the standard deviation is 27 pounds. And the distribution of weights of individuals on campus is approximately normal. So this is key, right? They tell us that it's normal. If a random sample of 16 persons from campus is taken, what happens? Okay, so notice that they said that we are normal, even though we are using 16 people. 16 is not safe enough to assume normality, so the fact that they have to say that is very, very important. So we know that our sample size is 16, our mean is 150, and our standard deviation is 27. So since we're talking about this distribution, okay, so let's look at A. So A says, what is the expected value of the distribution of the sample mean weight? Okay, so for A, the expected value, that's your mean. You know, what are we expecting out of that? You know, so that's, the expected value is the same thing as our mean, which is 150. That's it. So then we have B. It says, what is the standard deviation of the sampling distribution of the sample mean weight? Well, we know that our sample standard deviation, our standard deviation for our sampling distribution is going to be our normal standard deviation over the square root of n. So we just have to replace those things. So our normal standard deviation was 27. Our sample size was 16. The square root of 16 is 4. So we end up here with 6.75. So C says, what average weights for a sample of 16 people will result in the total weight exceeding the weight limit of 2,500 pounds. So if we have 16, so let's just solve. So if we have 16 people, and each of them has a average weight, so we're just going to say, we'll call it W bar. So their average weight, that has to be greater than 2,500 pounds. So it would follow that if we divided each side by 16, and we would have our average weight here would have to be 2,500 over 16, which that should be 2,500 over 16, 156.25 pounds. So that is what we are looking at right here. So our weight would have to be greater than 156.25 pounds. Now we go to D. What is the chance that a random sample of 16 people will exceed the weight limit? So the idea here is that in order to exceed the weight limit, the average of that sample of those 16 people, the whole average would have to be greater than that number. So we can actually use our sampling distribution to find that. Okay, sorry, I got distracted again. So the chance that a random sample of 16 people exceed this weight limit, which is we found to be 156.25. So this is going to be based off our sampling distribution. So we do the normal CDF, our lower bound. So the smallest is going to be 156.25. The top, we're going to say there is no top. I mean, realistically there would be, but we're just going to call it infinity. Our mean is going to be 150, and our standard deviation is going to be 6.75. So this, obviously, because we can see that this is about one standard deviation above the mean, so it's pretty small percentage chance. And so that would be, oops, let me load this back up. So we do our normal distribution, CDF, and so we do 156.25, yeah, 0.25, comma, and we do 1 e to the 99. That represents kind of like the largest number our calculator is going to deal with. That's just to be safe. And then we do 150 is our mean, and our standard deviation is 6.75. And we get 17%. So 17% roughly. Now, you may say, oh, that seems like pretty high. Well, that's if the elevator is completely maxed out with 16 people. If there are 16 people in an elevator, based off of this normal distribution, if it's all random, then there's a 17% chance that it exceeds the weight limit for the elevator. I don't know if that's a normal kind of mathematical thing for elevators, but oh well. But the main thing about these problems is that it's very similar to our last section where we were just dealing with the normal distribution. The big key is that our standard deviation for our samples our sampling distribution is going to be smaller, and it's going to be smaller by a factor of the square root of our sample size.